All right, guys, here we go. This video is going to go over U7 lesson 1 of graphing rational functions. Okay, so this warm up here where we have these 3 questions, I'm not really going to spend too much time on this. You can see the answers, but basically want you to be able to, add, subtract, multiply rational functions. So if you want to pause the video now and take a look at these, feel free. I will point out that C is probably the most relevant because we have some factoring and some canceling. But yeah, I think that's all I'm really going to say for that part. Okay. Moving on, right? Again, I mentioned in class that, ideally we do this as an investigation. We give you a little bit of time to think about this stuff, but, with it being the end of the year and with other things being a factor, basically, the main point of this is we want you to know what this kind of equation produces graphically, okay? And, just from earlier topics, right? Hopefully we remember that this A value right here, and I'm really sorry for this laser pointer, right? I don't know why it's kind of leaving this trail, but this value here, this A, we're multiplying the whole equation by that, and so that's going to produce a vertical stretch or a compression depending on, how big or small a value A is, okay? But to be quite honest, we're going to be able to figure out, like, using points what A does, and so it's not as important really in the graphs of these as what H and K do, okay? But that's really what A is. Okay, so H, right? So H, we're adding it directly next to X, okay? And we've talked about also before, when we add a number right next to X, it moves the graph left or right, okay? So this H, if we add H, the graph moves to the left H units. And if we subtract H, the graph moves to the right H units, okay? So that's good to remember. And really, in these graphs that we're looking at, the big significance of H, right? The big significance of H is that there will be a vertical asymptote. There will be a vertical asymptote when X equals negative H, okay? And the reason is, when X is negative H, this part is equal to 0, and so the whole graph will be undefined. Okay, now that's in this specific form. There is one other case, but we're not going to look at that now. Okay, and so I've given 2 examples. Let me erase this because I didn't put this in the full field notes. But if you look at this example where you have something over X minus 2, well, when X is 2, there will be a vertical asymptote. Okay, and if we have something over X plus 2, well, now X has to be negative 2 to make this denominator 0, and that will also produce a vertical asymptote. Okay? So basically, this is the key point, right? If X is equal to H, and I just realized, guys, I got to make a change here, right? It should be negative H because we want the denominator to be 0, okay? So if X is equal to negative H, the denominator is equal to 0, the function is undefined, and that means we have a vertical asymptote. I abbreviate with that with VA. We have a vertical asymptote at X equals negative H, okay? The one other thing that we have here is K, right? And so essentially, right, K is going to be your horizontal asymptote. That's ultimately what's going to happen, okay? And so, it's technically a vertical shift, but that's really the big idea, and I'll write that in here also, is that Y equals K is a horizontal asymptote. I hope I said horizontal, not vertical earlier, but yeah, it's horizontal. Okay? So, sorry, I wanted to highlight that. Y equals K is a horizontal asymptote, and then X equals negative H is a vertical asymptote. All right, we'll look at some graphs and what that means next, but those are the important characteristics really of this form, right? 2 important things. this is your horizontal asymptote, and then x being negative h will be your vertical asymptote. Okay, so let's look at some examples, all right? And here's a step-by-step way to graph these, which is, again, what we want you to be able to do is make graphs. But the first things, right, get the asymptotes. Okay, that's the most important thing. After that, we're gonna compute a couple points to guide the shape of the graph. That's really it. Okay, so this first example, we have -3 over x plus 3 plus 1. All right, got a couple things going on here. This one, right, this is the horizontal asymptote. So I've plotted that right here, right? We make asymptotes with these dotted lines, right? But that is our horizontal asymptote, okay? And in this denominator, if x is -3, it's equal to 0, so that's our vertical asymptote. Okay, so right away, that's the first thing I would do is I would graph this line, make it dotted, horizontal asymptote, graph this line, make it dotted, vertical asymptote, okay? And then, I gotta be careful with what I say, but number one, these vertical asymptotes, they will never get crossed, ever, okay? Horizontal asymptotes occasionally get crossed. The ones we're not gonna look at, they really won't, okay? But I'll show you later, if we have time, how to look for that. But because these don't get crossed, right? The graph can't cross these. All we have to do is basically pick one x value, right, on each side, maybe one here, see what the y is, and that's going to guide our graph. Okay, so on the right side here, I'm looking at, well, what happens when x is 0, right? We actually have the value here. So 0, 0 is a point. That's all I need to make this part of the graph, because I know that the graph is going to approach this vertical asymptote, okay, this way. So I've got that part. And because this point is below the horizontal asymptote, it's below here, the graph is going to approach that horizontal asymptote, but from below. That's it. Okay, so that point gives us this shape here. And then I chose -6. The y value is 2. So if I plot this again, I'm done. I got the graph, because I know the graph has to approach this vertical asymptote, and it has to approach this horizontal asymptote, right? It can't go across. It can't go down through here. So this is how the graph has to look, right, on the left side of that vertical asymptote. Okay, so that's really it, right? You get these 2 points from the equation, these 2 asymptotes, right? You plot a couple points, you see what happens, you make the graph. Easy. Okay, domain and range. So domain and range, sometimes it's easier for us to describe these in terms of what x can't be. Okay, so when I write x cannot equal -3 and y cannot equal 1, the assumption is everything else is okay, and we see that, right? Here's x equals -3. X can be everything else besides that, because it's getting close, super close to -3. Here it's going to the right forever. Here it's getting super close to -3, and it's going to the left forever. So x can be anything except for this vertical asymptote. And similarly, right, y can be anything except for this horizontal asymptote. Okay, and by the way, I might as well show you now, right? The way that we can check that this doesn't get crossed is we can set the equation of the horizontal asymptote 1 equal to the original function, and in this case we're going to see that there's no x that solves that. Okay, so if I just write 1 equals -3 over x plus 3 plus 1, right? So I'm taking this equation here, the equation for my graph, and this equation here, the equation for the horizontal asymptote. And look, guys, if we set these equal, these drop, okay, and we get something that can never happen. 0 is equal to -3 over x plus 3. This can never happen because -3 is never equal to 0. Okay, so therefore we know that this asymptote never gets crossed. So that's a check you can do if you want, right? In terms of your horizontal asymptote getting crossed. Okay, so those asymptotes, they guide the way we describe domain range. All right, and then the last thing, and I'm going to pause this video because I think it's been long enough, and I'll make a second one. But we're going to describe the behavior of the graph by using limit statements, okay? And so your general form for a limit statement, right? You have the limit, and you describe where x is going, and you describe that with an arrow. So this says the limit as x goes to infinity, okay? This says the limit as x goes to -infinity. All right, so here we're talking about what happens as we go way to the right on the graph. right? If x goes to infinity, we're going way to the right. Here, x is going to negative infinity, okay? So we are going way to the left on the graph. We're looking at what happens as the x values get, approach negative infinity, okay? On these limit statements, now these are a little bit more complicated, but x is going to -3, okay? And we'll talk about what this means in a second. X is also going to -3, okay? But if we look, right, there's really two scenarios when x is getting close to -3. There's one here, and there's one here, right? We're just talking about x values. So I'm tracing the graph, but really I'm just looking at what's the graph doing as I'm getting close to -3 that way and that way, okay? So the way we describe the sides, all right, I know it's a lot, but it's just a notation. If there's a negative on the number, right, and the number is an x value, which this is, right, x is going to -3. The negative means from the left, okay? So this x arrow -3 negative, that means that I'm looking at what's happening as I'm going to -3, but from the left side, okay? And from the left, I just follow this part of the graph, right? And I can see, well, as I go to -3 from the left, the y values are going to infinity, okay? So that's my answer here. This is what are the y values doing. X goes to -3 from the left, the y values are going to infinity, okay? This plus here means from the right. So this is saying the limit as x goes to -3 from the right, this is just the function that we're using, it's f of x, right? The y values approach negative infinity. So as x goes to -3 from the right, the y values go to negative infinity, okay? And we can see that. Here I'm following the graph and I'm going closer and closer to -3 from the right, but those y values, right, they're decreasing fast, right? They're going to negative infinity, all right? So it's confusing, but that's what a limit statement is. You say, where are the x values going? Okay, and again, we had infinity, negative infinity, and then two different cases for -3. This is always an x value. Then you just state which function you're looking at, okay? That's pretty easy. We called ours f of x. You can write the formula if you want, but this just saves you some time. But you have to tell, the reader what function you're using. And then this equals, right? This is a y value. And this is the y value that the y's are approaching, not equals. Okay, that's a big difference. Not equals, but what they're approaching. So the limit as x goes to infinity of the function is 1. Look what's happening. I'm letting x get bigger and bigger and bigger. It's going to positive infinity, and I'm following the function. The function values, the y values, are getting really, really close to 1. So that's my limit. Okay? So a limit, this is what a limit is. This describes what the y values approach. Okay, it's not necessarily what they equal. Okay, it's what they approach. Right? So with the horizontal asymptote, the y values get really, really close to 1. And with the vertical asymptote, the y values get close to either positive or negative infinity. Okay? So I'm going to stop the video there. I'll make a second one going through these examples, this different form, but that's it for the first video. Hope it was helpful.